David Henny from the University College in Cork. The title is indicated over there, and David, the stage is yours.
Okay, so thanks very much, and I'd like to thank the organisers for the opportunity to give a talk here. It's a very nice programme. So what I'm going to talk about is, as Joachim didn't read out, basically what we looked at is predicting the free surface elevation for waves using the pressure at the bed when one has vorticity. So it's essentially work in progress, kind of. So I was saying to people, breaking news and hopefully not fake news for our American friends. This might mean something. Okay, so there's been some very interesting recent work done about how one can recover the free surface profile using pressure measurements at the bed and elsewhere done recently. It's a long-standing topic, so hopefully I'll give an introduction, brief survey of results, and with Gareth Thomas that I've been working with the last 5 years, we have got a new reformulation of the equations and some new formulae, which hopefully, as I say, it's kind of work in progress, hopefully will be of interest to people here, and particularly it should be explored, well, hopefully with us numerically, but also for guys, there's some very good experimentalists here. Be very interesting if you could, well, if this problem interests you, I think it would be something worth testing, this new formula. Okay, so as I said, there's some experts here and other people who maybe don't know the problem, so determining the relationship between pressure distribution and wave surface, it's very interesting practically, but it's also very difficult. Physically, it's incredibly important because measuring the surface profile directly is not something that is trivial. You know, people can use satellite measurements, but it's not necessarily in real time, and it's a very non-trivial issue. So, what's often commonly employed alternative is to use pressure transducers at a certain fixed depth, often at the fixed bed, and one can hopefully calculate the free surface from this. But what this hinges on is what's called the pressure transfer function. So, okay, and obviously the key to the success of this approach, rather than trying to measure it in real time using whatever methods, I mean, obviously one can't measure the whole ocean in real time and it's not feasible. But pressure transducers apparently are relatively easily accessed these days, and one can employ them in the field, so it's a much better alternative than trying to measure them directly. And as this is a nonlinear water waves workshop, we care about the free surface and the wave. So the point of this talk is some, as I said, recent work with Gareth, where we look at the rotational setting where you have vorticity, but most theoretical and engineering works at this point have focused on the irrotational setting, and much of this is in the linear setting. And as I think many of us know at this stage, is that vorticity complicates things hugely. So it's not surprising that there's a very little literature in general for waves with vorticity. I mean, it really complicates matters a lot. And for the pressure transfer function, we just state that, as far as I know, there's a well-posedness, so it doesn't make sense to look at the pressure at the flat bed and you can recover a profile. This is, I think, only proved for solitary waves. As far as I'm aware, it's not for periodic. And in the irrotational setting, for nonlinear waves, this has been recent results due to Adrian and collaborators, so it's really mathematically very heavy. And as I say, applied engineering people are very interested in this. And, you know, it's typical in mathematics. Converse to the difficulties mathematically is the physical importance. Waves with vorticity are incredibly important. Any wave current interactions, one has vorticity. So when you're measuring perhaps the flow on a flat bed, the flat bed is well known as being a place where there's a lot of currents. You know, it accounts for sediment transport and other physical aspects. So, so I think it's important to try and approach including vorticity into the discussion, and it's a not trivial thing which took 5 years of discussion between myself and Gareth to try and get anything. And I think a love of sports helps and also detracts from ability to produce formulae, but finally we hopefully have some useful ones. Okay, so as I say, it's not just to go for the pressure transfer function, but what we found was successful was to try and get a general ability to get a relationship between the pressure distribution and the kinematics of the wave fields of a flow. And then one can, as a subset in a sense, recover the pressure transfer function. We believe we've derived a new pressure stream function formulation of the governor equations, and from this we get the distribution function. Okay, so, and as I say, this is fairly current work, and we're very receptive to comments and suggestions and any remarks. Okay, so governing equations, since this is the only picture that will appear, I decided I'd cheat and put a nice photograph. We're going to use two-dimensional fluid motion, which is fairly reasonable, and spatial periodicity. So this is not something I took on a beach, unlike Roberto. So this is something I stole it off the internet, but it's generally well regarded that ocean swell is two-dimensional and periodic until one goes to the surf region. So what we consider is essentially near shore from here to here, and then you've got far shore region. Okay, and as I say, this is a useful aspect of giving a talk in the last day of the workshop. Many very nice talks were given to this point, so I'm not going to dwell too long on the governing equations, but what we use is the Euler equation, so we assume the fluid is inviscid and incompressible, and we've the incompressibility equation. So U here is, so this is also an interesting aspect of, as a person with a more pure background, working with Gareth, who is the applied stroke engineering expertise, notation and language is a key tripping in many aspects of water waves. So in deference to him, I called U and W. I normally use U and V, it's lazy and it's easier, but and there's no Y, it's just Z. So, okay. P is the pressure distribution, rho is the density, so we assume it's fixed, and G is the usual just standard gravitational constant. Okay, so there's a big question in you know, as I say, what we were really aiming for was trying to get practical formulae that give you pressure recovery, which I'll outline a little bit, rather than more theoretical sort of investigations of waves with vorticity. So if you're looking for practical results, one has to fix reference frames and so on very carefully. So anyways, the mean water level is at 0. So it's the usual thing, the average over a wavelength is 0. The flat bed is at z equal to minus h. The depth is incredibly important in applications. Fixing the depth is incredibly important. If you don't fix the depth, well, for engineers and applied guys, this is essentially useless information. As I say, fake news. So at least we fix the depth. Okay. And we have the usual conditions that the flat bed is impermeable, so one doesn't have a flow through the bed, and we have the kinematic conditions and the dynamic condition on the surface. As I say, we try and get a new pressure stream function formulation, and the thing is, as many people know, and maybe the people who are coming here new don't really so much know, that one can transform the equations in terms of the stream function and you get a very nice condition. But what seems innocuous in the physical formulation that the P is constant on the free surface is really what complicates matters when you go to stream function and other formulations. It's essentially the Bernoulli constant. It retains the nonlinearity, and even though it's just a surface condition, it gives you the relationship between the pressure and the other variables. And as Robin gave in his talk, sometimes you cannot fix the pressure. It may be a variant. It's an interesting aspect of the modeling. We're looking at surface waves in the nearshore, so we can fix the pressure. So generally we take the constant to be PA. Okay, this is the hydrostatic pressure, but what we're interested in this problem is the dynamic pressure. So it says what is the pressure that's related to wave motion, which should be what's of interest, As I say, many people here people I know about vorticity, and other people maybe are less interested, and it depends, but the vorticity is incredibly important for describing wave current interactions. One can approximate things by irrotational flow, and that's also important. If you have irrotational flow, it's retained over time. But if you're really interested in wave current interactions, which is common in the nearshore region we're looking at and on the flat bed, you need vorticity. And in 2D, you get this simple formulation, which, it's worth emphasizing. It's related to currents. So if you have literally a current without a wave, and you have a variant in the wave field, so what you're left with is UZ. If you have a current which varies, this is vorticity. One needs it. So once you got waves, you have to incorporate this vertical component as well. But even without waves, for currents, you need vorticity. Okay, so a brief survey of why we're interested in this problem, why it's important. Just to say, as I say, people can do satellite imagery and measure the surface from this, but it's extremely expensive. It's very complicated, and it's not necessarily in real time, although it's actually very impressive at the same time. So for buoys in the ocean, or buoys, particularly for tsunami detection, but in general, they use this hydrostatic approximation, which is incredibly basic. If one wants to incorporate waves, which obviously I think we all agree at this stage in a nonlinear water waves conference is important, we have to complicate things. So for a rotational fluid where the vorticity is 0, we all know what vorticity is, but this really is a very special relationship when it's 0. UZ is equal to Vx. Following a basic linearization procedure, this is your ansatz per surface. So A is the amplitude, and it's the cosine kx minus omega t. We get this wave field solution, and this is your pressure distribution. So I highlighted in red. There's a direct correspondence between the dynamic pressure and the wave field. Okay, so A is the wave amplitude, K is the wave number, which is 2 pi divided by the wavelength, and omega is the frequency. And I'll mention a little later. Sorry, these guys aren't independent. They're related by a dispersion relation, which is non-trivial. For linear waves, it comes out nicely. It's a very interesting thing. It gives you a lot of physical information. Dispersion relation, even though it's a simple relation, it's incredibly interesting. And for what we do, you can add extra terms and it becomes even more interesting. So, okay, anyway, so comparing 3 and 4, you get that this wave surface is related to the pressure, the dynamic pressure at some fixed depth by this relation here. And Kp happens to have a nice formula. So it's the hyperbolic cosine with the z component here, and here this is fixed. And this Kp is called the pressure response factor. So this was derived many, many years ago by engineers essentially. And there's been some recent work which have investigated how one can incorporate nonlinearity. Just to say, when we went to vorticity, there's people here who've looked at vorticity, and it's incredibly complicated in general, but for this. So what happens is we look at what's called the amplification factor. It turns out this amplification factor Q of Z it's basically what's the ratio of the depth at the surface. We look primarily at linear waves, so 0 is the surface, and the depth at some, or sorry, the pressure at some depth, the dynamic pressure, where you decompose this regular wave term. And what one has is you can get that the free surface is the amplification factor times, this is why it's called amplification factor, times the dynamic pressure with this quantity here. But basically this pressure response factor is what engineers essentially study and have studied. And yeah, what we look at mathematically, what's more pertinent is the Q of Z, the amplification factor, and that's 1 over Kp. Okay, so this transfer function formula was derived many years ago, and it's been the subject of much debate in engineering literature. There's very, very, very nice field experiments and data. So one paper that's very pertinent is Bishop and Donnellan. It's a survey paper where they compile many other arguments. And for, as I said, originally pure mathematician working in more applied areas, it's very interesting that engineers really attack each other in papers directly. So there's some people who said that one should multiply by a coefficient, and then there's other people from the same country who say that in a very good journal that this is all absolute rubbish and explicitly mention them. So even in the linear case, this is a subject of much debate. Even though it's okay, for irrotational waves, it's quite a simple formulation. It comes from really this linear ansatz, and one gets from this expression that we have this pressure response factor. It has been recognized that it's actually a very accurate formula for most waves. But when you get to large amplitude waves, you need to take into account nonlinearity, and this is where people have discrepancies. Also, another thing which has been considered is that should it be at the flat bed or at a fixed depth? Because the bed, there's sediment transport, there's surface, or there's shear flows at the bed, so perhaps it's better above the bed and at a fixed depth. So this has been considered in great detail by numerous papers in engineering literature. And thankfully, mathematically, this formula applies also not just for the bed, but at some depth. Okay, so it could be, okay, how it's practicable is another matter, but at least from a formulaic viewpoint from mathematics, it's interesting. And okay, for nonlinear effects, very little, as far as I'm aware, was done until very recently. So Joachim and his colleague did a nice, interesting work in sort of investigating this area, and Adrian and his collaborators did some exact formulas for proper nonlinear waves of any amplitude up to the essentially Stokes wave of greatest height. So for solitary and periodic, and also Florian extended this to periodic, very nice result. And there's a nice paper by these guys from the States, and Diane did some very nice experimental work for the solitary wave case, where one can compare the formulae to the measurements. So there's been some very recent work. As far as I'm aware, I don't think there was any nonlinear work until the last decade, but some very nice formulae which have been compared to experiments and numerically have been tested. So. And, you know, when you go beyond a certain regime, one needs to take into account nonlinear effects. But the whole point of this talk, as far as I'm aware, is most of the literature until recently focuses on and depends heavily on the irrotationality of the fluid. Once you've got vorticity, things are destroyed. With this solution, everything hinges on uz is equal to Vx from just comparing them. Once you've got this, things are ruined. So there's been some nice work. Sam has, with collaborators and in this paper and others, worked on some aspects of with vorticity, and Oliveros and Vasson have looked at some reformulation thing. And this is a paper where I look at the well-posedness, but just for solitary waves. So it's incredibly complex from a mathematical viewpoint that it's even well-posed. So, you know, this is really a step into the unknown, or has been, I think. And like I say, this is it's current work, and really we welcome comments. Okay, so this is going over old ground maybe, but when you've got flows with vorticity, you've no potential. So you have to just find a stream function as such. Okay, and the Laplace, so this nabla squared is the Laplace operator in 2D of the stream function is the vorticity. Okay, so omega is your vorticity here. So defining the stream function, what's typically done, and it's related a little to the talk Gareth gave in Monday, is that what's often done is you look at the Helmholtz vorticity equation. And what we're interested in is regular waves. In engineering terminology, what I think mathematicians call steady waves, so they're periodic and they have a constant wave speed. So essentially the xt dependence is as such. Okay, so k is the wave number and omega is the frequency, so it's a regular periodic wave. Okay, we can reduce the Helmholtz equation to this. And this equation is used a lot for numerics and stuff. It was used a lot by Dean Dalrymple, one with irrotationality and one with vorticity, to look at aspects of the wave kinematics. But the point is, as I think many people know, is you often kill out the pressure. There's no direct relationship between the stream function and the pressure here. Okay, you can recover it through the Bernoulli condition, but it's essentially lost in this equation here. So what we decided, it wasn't decided for us. After hitting brick walls, we went back and we looked directly at the Euler equations to try and get something with the transfer function with vorticity. Okay, so with some manipulations, the Euler equations can be written as such. So H is this equation here. So it's something which in a sense can be integrated, and these are the terms which aren't directly integrable. Contains some vorticity here, and basically all these terms on the right hand side are rotational. They include the vorticity. Okay, nabla squared psi is vorticity, and these are various derivatives. And this formulation is interesting. It can be related to the Bernoulli condition if one wishes, but for what we were looking at, we just worked with this. Okay, so the terms not included in H, we can write them as minus f minus g for convenience. Okay, so these guys here, and we integrate directly, and it's formal, but we integrate with respect to theta, we call this guy f, and with respect to z, we call this g, so we get these guys. Okay, we just say if we were to integrate this guy with respect to theta, this guy with respect to z, formally these relations are fine. So in principle, we should be able to establish what a, z, and b theta are like. And in the absence of analytic or exact solutions, this is still not trivial. And, you know, these are not things you throw away. They really physically make a big difference. They represent mean flow contributions for currents and waves. So when one is looking for essentially exact solutions to some extent without doing a truncation of the series in the sense of the Stokes wave sort of expansions, we try and use a formal infinite series expansion. Okay, so this is your psi, the stream function, we call it little psi n, and this is your regular wave profile, and this is your pressure. And also the vorticity, it's obviously in these terms written in a fairly straightforward manner. Sometimes we use the psi n double prime, and these guys are sometimes use the omega n. So omega is our vorticity. Okay, so the point of this is that analytic solutions, basically there's some very nice existing results due to Adrian and Walter on existence of water waves with very, very general vorticity distributions, and this has been generalized by numerous people in the audience. There was original work done by Dalrymple and others on like linear profiles with linear shear currents, etc. But it's a very non-trivial question whether solutions exist at all. Hoping for analytic or exact solutions is not something that really we've any right to expect. And in the sense that this is correct, is that only when omega 0 is 0 or constant we can get analytic solutions. So basically in the rotational case you can get exact solutions. From these guys here we can identify the hydrostatic component. So essentially what is interesting is the dynamic pressure, but from this formula too we ignore the hydrostatic. Okay, so we don't really care about that. It can be recovered easily, and from this formula here, this is your H, these are with respect to different variables formulae, so we have this relation here. Okay, so following a lot of computation, these are your formulae. Okay, so essentially what we're interested in is these guys, so it's the integral of f, integral of g. Az is the current term, it depends on depth, and H is this interesting guy too. So H, we can write it like this, which is, so Gareth said, I'm not going to pay for the coffee, so he will, for people who remember all of these formulae at the end of the talk. Okay, so this is your H. It's even though it's complex, it's miraculous that it has this relatively succinct form. Okay, it's double indices, but still relatively succinct. This integral here is a relatively nicer form, and G. If you want the details, by the way, I'm not going to kill you with details, so I can send you it afterwards. Integral of G is very complex. Okay, but these things can be plugged into this new pressure stream function formulation, and we get proper relations. Okay, so this Az term is related to how the current behaves, and as we say, if you're interested in vorticity, it's primarily due to currents. So Az, this A0 is a constant that's determined by physical conditions. It's related to the mean flow quantities. It's not necessarily due to the wave characteristics. When you're dealing with these series, and primarily our result is linear, one has to decompose the current and the wave fields to some extent, although I'll mention how we have an interaction. And for rotational motion, this constant A0 is essentially related to the Bernoulli constant. Okay, so it's a kind of a generalization in a formal infinite series sense of the Bernoulli constant for waves of vorticity, which is, I think, fairly interesting. Okay, so hierarchy of series harmonics. There was a debate of whether this should be series or serious, because it took many weeks. It wasn't trivial. So this is our expression of how one can relate the pressure to various relations involving the stream function and the vorticity, which is obviously defined in terms of the stream function. And this is, like I mean, it's miraculously succinct. It fits in one slide, but it's not exactly tractable in the sense it's in. So the next step for us is to match the components on each side. So the n equal to 0 term, so B0 is where there's no wave, it's the sort of underlying current. So we have this relation here, and we can see that vorticity is obviously very important. It occurs, well, the omega terms here. And what's surprising is when the vorticity is 0, the base vorticity, so initially when omega 0 is 0, the other guys have to be, it's irrotational, the pressure can be given by this, which is the dynamic pressure. So it's very interesting. In the irrotational case, we have an explicit expression for the dynamic pressure. But typically, in this case, you use a velocity potential rather than a stream function. If omega 0 is constant, then the current has to possess a linear profile. So the wave is irrotational because one can decompose because it's a linear profile, one can decompose the wave from the current at this level, and we get this expression. Okay, so analytic solutions in this case are far from trivial, but this is the sort of Fenton and collaborators type Stokes expansion, which apparently doesn't work up to fifth order, but at third order was accurate. Okay, and when omega 0 is arbitrary, the base vorticity, and then essentially these guys do not vanish, we have, I mean, from this expression here and this expression, funny enough, they look far more complex than when you actually have vorticity. So somehow when your vorticity is naturally suited to discussing the pressure without a wave, which is quite interesting and unexpected. Okay, so this A0 is not just a random constant, it's physically very important. It has to be chosen so that the surface pressure is 0. Okay, so this is your general scheme. That's the 0 order terms, and this is our fairly complex looking, potentially infinite and nonlinear series. So for people interested in waves, at the first step, the linear wave is when n is equal to 1. So this is what we've primarily focused on. So for first order solution, when you've linear waves, given a current at the basic regime as I draw there, uz is 0, 0, then you've got y0 determined immediately by the integral of this current. In practical terms, most currents, I mean, the main important currents are tides, things like this, and as Gareth gave in this talk, there's various experiments. You've got waves with currents. Often it looks like a linear sheared current, or it's almost constant. So it isn't an impediment in a practical sense that we put a form on the current to get the vorticity. And obviously, if you know what vorticity you like, you can easily prescribe it. So what's interesting is from this infinite series with this new formulation, we have this description of the linear wave field pressure term, P1Z. So this gives us a direct pressure stream function relation which describes the wave field kinematics. We have this wave, or we have a surface condition, we have various things, but the point is it's described in terms of psi, so how does one find psi? Okay, so you have the Rayleigh equation approach, the stream function version. This is, as was mentioned in a number of talks, the stream function version. It's a second order ODE in the psi1. Potentially, if you can solve this, which can basically be solved in only a couple of cases analytically, but can be solved numerically, you have your psi1 and you can plug it into this somehow. So this is called Rayleigh equation or Sommerfeld in the inviscid theory, and you've got various boundary conditions. The boundary condition, okay, so these aren't so important, but what we have is that the psi1 is proportional to A. What's interesting, and something I hadn't been aware of before, is there's a nice survey paper by Peregrine, and it's discussed a little bit in a survey paper by Gareth and Klopman, where there's a pressure version of the Rayleigh equation, and this is rarely invoked. It's derived a little differently than the other one. It's a little less trivial, but it's by similar principles. So instead of this second order ODE in terms of psi1, which is the stream function, you have a second order ODE in terms of the pressure. This is very interesting. Looks like it should be solvable, but not really in most cases. And these boundary conditions are given by Peregrine, bar the one at the bed here, which one needs to impose to be able to solve it. So solving this, I mean, so Peregrine surveys some nice examples of where it can be solved in very simple cases. Basically, the cases it can be solved is where you have a constant current and a linear profile. So the wave field is irrotational if you regard the current as being separate. But what's also interesting is, from a fundamental viewpoint, if you want to build from these simple profiles, that many current profiles can be approximated by these guys matched up with appropriate boundary conditions. So if you use Z as arbitrary, if it doesn't follow these guys, you need a numerical solution. And apparently for the pressure equation, this is well posed numerically. And there's a nice paper by Gareth on nonlinear waves where he looks at the string function form, so what we all would know. And this is not trivial, that it's well posed. So that's what caught us for a while. We were looking a lot of trying to look at this equation before we found the pressure stream function formulation. Okay, so this is, I mean, quite complex. One needs to look at the string function. It's not trivial. So what we're interested in is obviously the pressure recovery problem. So when you focus on this, what we want is we want to measure the pressure at the bed. And as I mentioned, this doesn't have to be the bed, it can be at an arbitrary depth. And we want to get the surface amplitude. Okay, so since psi1 from these conditions here, it's proportional to A, we can decompose it as A times chi1. And from the new equation, I think, as far as we're aware, it's fairly new, this relationship here. Okay, so it doesn't involve an ODE and B, but it involves the psi1s. This guy is psi1 to second order, but so we're interested in feedback if people are aware of it or have seen it. But as far as we're new, it's a new formulation. From this, we can plug things in and we get this relation. So if the pressure at the bed is a known quantity, then we can find the amplitude this way. And this psi1 prime, through the various equations, can be recovered without knowing the amplitude. So in principle, we get the amplitude of a wave with vorticity through this formula. And like I said, the amplification factor is this Q minus H. So this is the ratio at the surface to at some depth minus H, but this can be at any arbitrary depth in between. So as I say here, and I skip details, but it's a little more complex. One doesn't have such, you have a little extra terms, but they're not too complicated. You can do this at arbitrary depths and not necessarily at the flat bed, which is important. In this survey paper, the engineers, Bishop and Donlan, they do some nice survey and they say, okay, should one vary the recovery factor by depending on what depth you take it? And they say it's in fairly good agreement, but it may be useful. But one thing they put down to the variation between experiment and the theory is meniscus effects and currents. So in the ocean, you don't have too many meniscus effects, so the currents are hopefully the more relevant things that we're taking care of. So we can vary it with depth. And you know, I threw down the irrotational wave solution, but just to say that at minus h for the simple case, this q of minus h is the hyperbolic cosine kh. In the irrotational setting here, this is the underlying current, so u is 0. You've got c, and you've got this chi prime. Okay, so chi prime is eventually this guy. Since we know how u is in the irrotational setting, it's well defined in the linear case. And the magic, the little thing that maybe is thrown away by some people, but is probably, to my mind, one of the most important relations in water wave, the dispersion relations, tells us how things behave in a very succinct form physically. In this case, we know how omega looks, so you plug it in and you get q minus h, and magically things cancel and you get the hyperbolic cosine. And this works also when you've got arbitrary depth. So it is a proper generalization of the typical pressure transfer formula for irrotational waves. Okay, so the last part of the talk is the so-called moderate current approximation, where things get even more fun for people who like asymptotic expansions. So, numerical solutions are incredibly convenient and important, but from these equations, as I mentioned, there's very little analytic solutions. It's only for the very simple current cases. So this formula is useful, but as I said, this is really current work, and for people who do numerics, we're very interested in talking with people and experiments, etc. It'd be very nice to test these formulae. But from a mathematical viewpoint, there's no exact solution, no analytic solution. So it's hard from a formula alone to get insights. So there's a very nice approach, which is a so-called moderate current approximation, which was developed by John Hunt, and Kirby and Chen have a nice paper on it where they got certain things wrong, apparently. Hold on, if the microphone's on, I shouldn't say that, but and Thomas and Klopman, they have a proper formulation of this approach, where what's important is not alone does one have to have a proper matching boundary conditions, but we have an expansion in two parameters, not just in the physical variables or the stream function, but also in the frequency. So the dispersion relation is something which needs to be asymptotic also. Okay, so the parameters we employ are the typical wave steepness epsilon, and delta here is a measure of the strength of the current. So this is a characteristic current measure u hat, and divided by c, which is the wave speed. So when epsilon is small, which is typical for a linear regime, which we've discussed already, but also the current is not exactly tiny, but moderate, hence the name. It's less than 1. Obviously, the wave speed will be generally far greater than the particle trajectories in general. This is a moderate current approximation. The strong current approximation is where we don't make any distinction between the potential underlying current, which was the first order. Okay, so it's a further approximation. And just to say too, this hierarchy solution potentially enables people to get nonlinear. I'm just presenting linear results, but potentially one can get nonlinear relations, but they, I imagine, will be they'll be hard to fit in a slide. Okay, so perturbation solutions we expand in terms of the wave. Epsilon represents, in a sense, the wave, and delta represents the current. So we have these expansions, double expansions in terms of the delta and epsilon terms. So setting delta equal to 0 removes the imposed current, but it gives you wave solutions. Setting epsilon 0 corresponds to a current without, epsilon 0, there's no waves, there's just a current. So the interaction terms is, in a sense, what we're interested in, to get wave current interactions and to get vorticity. And this is a peculiar thing which complicates matters, but it's a nice way actually of generalizing the dispersion relation that one typically gets in just linear settings. You can get nice dispersion relations which are, in a sense, more nonlinear by invoking this expansion. So I haven't included them since we're at the point of the talk. Okay, so we rephrase how the current looks like. So V here is same dimensions as current, but it's comparable to the phase speed. So psi 0, 1 is the basic current term without a wave. This is trivial by this. Okay, U is the current. With waves alone, without any current, it satisfies Laplacian. So the solution I gave earlier, this is the solution. It's the typical irrotational wave solution with slight variance on the frequency related to this, which is important, but okay. And then we can recover the pressure from that, so P10 is recoverable. So psi 0, 1 and psi 10 are known. And the main interaction term and the stream function component for that term, psi 11, was previously obtained, and this is the formulation, which is complex, but it has an analytic formulation, if not something one can compute directly. Okay, so basically it involves these the current and these hyperbolic sines, cosines, and we have a relatively concise formulation. For pressure stream function kinematics, it's not necessarily trivial. One needs numerics, but the point is, for the pressure recovery formulation, we can go to what we did previously relating the pressure and the stream function, and we get this formulation here at this regime. H is the equivalent of what we had called H previously. Okay, so we get this formulation, and even the most optimistic people, I think, in the room would not think you can get a nice or solution of this, but believe it or not, we can. This is your solution. P11 can be written in terms of these derivatives. Okay, so this is in the approximate regime. We can recover the physical, reverting back to physical coordinates and non-dimensionalization. We get this is the pressure formula at this level for the wave current interaction. Okay, and what's interesting is, to one extent, one thing that worth mentioning is this term vanishes at the flat bed if we measure at the flat bed, because at the flat bed the stream function is generally always taken to be 0. So actually we don't involve even derivatives of the current, which is apparently numerically quite complex to have derivatives. So we really have the current here, and this is a stream function. And what's nice about this expansion is that you have the same dependency in terms of, for regular waves, in terms of x and t. So this theta, the phase function, we can decompose the pressure like this. We ran out of letters, so we use capital pi. Also a problem with water waves, finding the right letter, even Greek. So this capital pi is what we're interested in. It's the pressure dependency on the z. And the big difference is now this P is really known. It can be evaluated. Okay. I haven't skipped details. It can be evaluated, this capital pi z. So that's the pressure stream function kinematic relationship. For pressure recovery, what we have is, in the moderate current approximation, we get this very nice relationship here, and the pressure amplification factor is this Q. So really, all of these are known, and we can compute them in that regime. Maybe not analytically. This is why we like experimentalists and numerics guys, if they're interested, to help us. And, you know, the reason for this expansion, which is invoked for other reasons, but it really gives a very nice, succinct, and explicit expression for this pressure recovery formula, is that all these terms are known and can be, for a given profile, evaluated. As I mentioned before, this guy vanishes if you evaluate at the flat bed. If you don't, it can be included, but it adds an extra complication. And there's no restriction on the depth, as with the other formula, which is important in practical terms, as well as, you know, I mean, theoretically it's also interesting that one does not have to be necessarily at the bed, even though that's where, for practical reasons, many of these transducers are laid. But we can have it at an arbitrary depth. So essentially, like I said, this is work in progress, and recently finished some results, and hopefully if people are interested, we're very happy to talk and very interested in discussing this with people who can perhaps help with some of the verifications of these results. Okay, so thanks very much for your attention. Yeah.
Thank you very much. There is time left for remarks or questions.
Okay, I have one. A rather practical question. If I've interpreted this correctly, you need to know the psi function to be able to determine pressure. And that requires you to know what the current is, what the structure of the flow is below the surface. In practice, is it possible to get hold of that information?
Yeah, generally for most currents.
I mean, that can be measured fairly accurately.
Yeah.
So you can then interpret what the psi has got to be to then give you the pressure. But both those things have got to be done, i.e. you've got to measure the pressure, but you've also got to know what the current is and its said structure to be able to proceed.
Exactly.
But in practice that can be done reasonably well.
Yeah, reasonably well. And I mean, even theoretically, you know.
I'm not worried about the theory.
No, but I mean, even related to your talk, you can impose a current that matches a little bit
Yes, exactly.
what one expects.
So really the question becomes, is that good enough? Yes, of course you can reasonably match currents and basic structure, but is that good enough to get you sufficiently accurate surface profiles based on the pressure measurement?
This is, hopefully.
Okay, all right. Okay.
This is why we're looking for
Some input.
breaking news, as I said. Yeah.
Okay, thank
And
you.
hopefully not fake news. So.
Thank you.
No, but it's a little. No, many of the currents are, you know, I mean, one can impose currents that you expect. In your case, it's more complex, the EUC, but no, in general, you have waves against an opposing current, and the other way around, it's linear sheared and flat. So I think
and that's a reasonable representation of what is seen in practice.
yeah, hopefully.
Okay.
No, really. Yeah, this is why it's okay. Maybe I should have talked about something else, but no, it's
Okay.
why I talked about it here. We're really happy to have input from people, and it's something. I mean, that can be verified basically experimentally or numerically, not from the formula, and that's why we're very happy for input. But yeah,
Okay.
yeah, no, thanks. That's a good question.
Right. So you mentioned that in experimental results there were discrepancies between the recovery of the surface profile from bottom pressure recorders due potentially to meniscus effects and currents. So how big are those discrepancies? So if you're thinking of improving this by including effects of vorticity, what kind of actual improvements are we talking about quantitatively?
100%. Okay, now I'll turn off the mic.
You have a negative wave, and then actually the pressure tells you the positive wave. 100% improvement.
Yeah.
So I mean,
200%.
yes.
What sort of question? I mean, reading some of the survey articles is brilliant. You've guys tearing each other apart with the same experimental data. I mean, okay, mathematics, at least, there should be right or wrong at the basic level. Engineering is brilliant. You're a converted engineer, so you can tell me.
I'm asking. So.
Yeah. 300%. Right answer. Okay.
Okay, please.
So your solution depends on two small parameters, epsilon and delta.
Well, the approximate solution, the other one doesn't. It's a linear thing. In principle, you can go to non-linear, but you just, yeah.
So I can guess how you can choose a epsilon depending upon physical setting, what the small parameter might be. For the current, what would you have any suggestion on what kind of physical?
In that regime, it's a lot smaller.
Delta.
Delta, yeah, but in general, one would expect the wave speed to be far stronger than the current anyways. The underlying current, I mean, is like particle trajectories. Generally, the wave speed is, I think, like 9 times or 10 times stronger than the magnitude of the current, or sorry, the particle trajectories without a current. So generally, this is not a physically implausible approximation by any means. But exact figures, depends on the context. And this is something we have to pursue to try and match data sets and stuff. But yeah, so it's not atypical that delta would be small.
How many measurements do we need for reconstruction of the surface?
Yeah, well,
2, 3, 4, 5?
yeah.
5?
Yeah, you tell me.
Some fine number.
I think it depends. As I said, the only recent experimental work from someone I've met personally was Diane Henderson from Penn State, and she did very nice experimental work on solitary waves in a wave tank. I think it was a fairly small wave flume. I think she's something like 10 or 15 pressure transducers, if I remember. And so, but I mean, apparently pressure transducers have recently become relatively inexpensive, so this is not the problem. This is a theoretical formula, but obviously in practice one approximates if you're doing numerics or experiments. So depends on your where you're measuring, but